Hi, I'm Jackie Cation. Welcome to NASA's Universe Unplugged live chat, where NASA scientists are here to answer your questions about our videos where the stories are fiction, but the science is real. Today we're talking about the formations of stars, as seen on our video, Think Tank, A Star is Born. You can find our links to our YouTube channel on universeunplugged.org, as well as all sorts of bonus information and downloads for each of our videos. Never miss an episode if you just subscribe to us on YouTube and follow us on Facebook to join future live shows, because we're live. We're live today, you guys. Today, we are joined by Dr. Louisa Rebel, who is a scientist at NASA's Infrared Science Archive. Her research focuses on star formation and, in particular, the rotation and variability of young stars. And she also leads the NASA IPAC Teacher Archive research program. Welcome to the show, Dr. Louisa Rebel.
Hi, thanks for having me.
There you go. We are also joined by Dr. Roberta Paladini, who is a scientist working on one of NASA's next astronomy space missions called Sphere X. Her research interests include massive star formation and studying the dust and gas between stars where star formation takes place. Welcome, Dr. Roberta Paladini.
Hi. Thank you, everybody.
Okay, let's start with a clip from A Star is Born before we dive into the questions, so you get an idea.
Welcome back to Think Tank. Today's topic is starbirth.
Alternate title, A Star is Born.
Very catchy. Is the thought visualizer ready?
All set, boss.
Let's do our tech check. Think of a light wave. We'll have to work on that. Every star begins its brilliant life as an enormous dark cloud of gas and dust. This cloud is very cold, drifting and rotating through interstellar space.
Exactly. Wait, why is it rotating?
Well, you're hard-pressed to find something in the universe that isn't rotating to some degree.
All right, checks out.
Anyway, sometimes gravity can pull the dusty cloud closer and closer together, which can collapse under its own weight.
Ah, it's crushing me.
Space clouds don't feel pain.
Okay, so let's quickly review. Louisa, would you review what makes a star shine?
So when a star is actually, when you can actually call it a star, like a fully adult mortgage-paying adult star, right? That's when it's actually burning hydrogen, by which I mean a thermonuclear reaction is happening in the core of the star and is turning hydrogen into helium. So when we talk about a star formation, how stars form, we're talking about everything prior to that ignition of hydrogen in the core of the star.
Okay, and so when it shines, it's that fusion.
Is the fusion? Yes.
The fusion that is, hello, I've gotten a word right. It's the fusion putting off the energy, which is creating the light.
Yeah, it's the source of energy in the center of the star is where it's turning hydrogen into helium.
Okay, so now both of you, let's go with Roberta. Where are stars born?
So as the video that we have just seen was saying, so stars are born in very dense and cold regions of the galaxy. So think about having a ball of gas and dust. If it is warm, all the molecules and the dust are going to be basically flying around, and they will not be able to collapse in one place. But if this place is very cold and very dense, then the molecules will be forced to collapse in one place under the force of gravity. So we basically allow gravity to make it work. And so this is why we want to basically to find this place in the galaxy which are really cold and very dense, because only in these places we can actually have the formation of stars. And these are the places that we call giant molecular clouds. So these are very massive clouds. So these are not traditional clouds in the galaxy, but these are very massive clouds of hundreds of thousands of solar masses. And that's where the formation of stars occurs. And yes.
Okay, so let me see. Louisa, do you have anything to add? That might...
No, I think she covered that.
Okay, so here's my question. So in warmer parts of the galaxy, there is the molecules, they disperse. They don't collapse. They don't huddle for warmth, essentially. Is that what they're doing? Are they just sort of becoming more and more dense because they're super cold and they're like, let's spoon, let's cuddle?
Right.
And okay. Interesting.
So,
Okay,
when an astrophysicist says temperature, she means the average speed of the particles. So when you have something that's warm, the particles are flying around at relatively high speeds. And you can imagine a high-speed collision is going to send the results of that collision everywhere. But a slow-speed collision, like two cars hitting slowly, will stick, right? They might throw off some matter, but a slower collision is going to stick together. And so that's part of why stars need to form in cold and dark places.
Okay, so so they're inside a cloud, a cocoon with a dust and gas, which is just made up of different particles of different solar. What is the dust?
So when astronomers say, when we look at the periodic table, we see hydrogen and helium and then everything else. And we refer to everything else as metals, just, because there's so little of everything else, right? The universe is 3/4 hydrogen and 1/4 helium and just a little bit of everything else. And those little bits of everything else matter a lot for forming dust.
Okay, so how can we study starbirth if they're cocooned in that dust and gas cloud?
You have to use long wavelengths of light, because the long wavelengths of light, like infrared, which is sort of redder than red light, the long wavelengths manage to make it through the dust. So sort of like when the sun sets, it's night, a really beautiful sunset will be very, very red and it'll be gorgeous to look at. But that same physics happens everywhere in the universe. So you get a really gorgeous sunset when you have a lot of stuff like dust from a volcano or something along those lines, lots of particles in the atmosphere. So if you have lots and lots of particles in your interstellar cloud, in your cocoon of matter, only the red light makes it through easily. So you need to go as long wavelength as you can, basically. And that's what infrared is really powerful for, is seeing into these cocoons of gas and dust that are too dark for us to see through in invisible light.
Okay. I have a weird follow-up question, but I think it'll link in, because Roberta, where do we find most of the dust and gas clouds in the sky?
Yeah, so as I was mentioning before, so basically these very dense and cold regions are in these giant molecular clouds. But within giant molecular clouds, we are the so-called filaments. So filaments are like, for a human body, like our skeleton. So if we had to describe where our backbone, the backbone of our body is, that's where the skeleton is. And the skeleton of a galaxy are basically the filaments where this very cold and dense material is sitting. That's where the star formation is taking place. And these filaments can be seen, as Louisa was saying, with with infrared detectors. We had Spitzer was one of the detectors that could see this cold dust. But even more than Spitzer, Herschel was another one of these telescopes that was really able to trace filaments all over the sky. And filaments are very funny creatures. I'm actually passionate about filaments because they are like living animals. So they have basically like a main structure, like our bones. So they have like a main structure, and then they have smaller structures that are called striations that basically feed into the main one. And these smaller structures are very important because they're basically channels that feed into the main filament the material that is going to be used to form the star. So basically when the star is born, it starts accreting material from the outside environment through these striations that accrete inside the filament. And then slowly there is a creation of what is called accretion disk locally. And then slowly the star is formed. So it's a star formation process is what we call a multi-scale process. So it happens across the galaxy on many different scales. So on very large scales and then on very small scales. So that's one of the fascinating things about studying star formation. We can really study it on many, many different scales and on many different wavelengths and looking at many different types of phenomena.
And the pictures
so
of the filaments that Spitzer has are just gorgeous. I mean, you could just scroll through the pictures of the galactic plane, and there's all the sinuous ones. There's ones that look like snakes or dragons as they curve around. They're really gorgeous.
Okay. So you're sending out infrared. So the Spitzer or the Herschel telescope sends out infrared light that pierces.
It doesn't send out.
Gas.
No, it's just watching. Your eyes don't send out light.
Watching.
Yeah, your eyes don't send out light. The light from other things, goes into your eye, and that enables you to see it. Right. So same thing with Spitzer or Herschel. They're watching the light.
And we're getting. This is why I'm here. So the infrared light that is coming back, the information that's coming back from these stars being formed is infrared light. That's where we're getting the information from.
It emits light at many different wavelengths, but the thing that the infrared makes it through, and things like X-rays and ultraviolet light and even optical light are blocked by the cocoon. So the infrared is the easiest way to penetrate the gas and dust.
Okay, and so we're getting most of our info. Go ahead.
You can think of Spitzer or Herschel like your own eyes. Your own eyes are detectors, and but your own eyes, they filter just some light, which is the visible light. Your eyes are not sensitive to any other types of light. They're not sensitive to X-rays, to infrared light, to any other light, only to visible light. Infrared and Spitzer and Herschel are instead sensitive to infrared light. So they are not sensitive to any other light but infrared. So this kind of phenomena that we are watching, they emit at many different type of wavelengths, but Spitzer and Herschel can only detect infrared light, like your eyes can only detect visible light. So
this is fascinating. We seriously do not have enough information. I would like to talk to each of you for hours on end, but let me just do a quick people, if you missed the beginning of the show, we're chatting about the science in the NASA video, Think Tank, A Star is Born, which you can see at universeunplugged.org, or just click on the link in the comments. We have a question, I think from the internet, which is, how about star formations in other galaxies?
Oh, absolutely.
Have we only been discussing our galaxy? What are we doing?
Well, I'm biased because I study things in our galaxy, as does Roberta, right? So that's what we love to study, is stuff in our galaxy. But absolutely, there's star formation going on in other galaxies, and a lot of it is very similar to the kinds of star formation that we see here. But because other galaxies are so far away, the star formation that we see in other galaxies tends to be the brightest and the biggest and the most substantial complexes. Whereas here in our galaxy, we can study things that are sort of more quiescent, calmer regions, sort of like the suburbs rather than the inner city.
Right.
We can sort of study it in a different scale of things than when you see in other galaxies, because the other galaxies are so far away, you're stuck with the biggest, brightest things.
Okay, and we're talking now about the creation of stars, right?
Mm-hmm.
So all of the items that are all of the debris, but it isn't debris, but everything is incorporated to make the star, right? Whatever the filaments.
You can think of it as debris because it's star guts, right? In order to get anything beyond hydrogen and helium, the matter had to have gone through a star. It had to have gone through a supernova. And so in that sense, it is debris. Anything other than hydrogen, helium is debris. Like Carl Sagan said, we are all star stuff, right? So the gold in our rings, the diamonds in our jewelry, all of that comes from stars.
Okay. And then it consolidates, or as Roberta put, it gathers together to create. Yeah.
Yeah. So basically, when you have when you start forming a star, one of the key ingredients is the accretion disk. So you have basically to make an easy picture, like a ball of material with this accreting stuff around it that slowly fall into the stars.
We used to be able to say like a record or a compact disc, but those are kind of obsolete technologies now. But you still get the idea. A disc.
Anything that spins, okay.
That is spinning. Now, that accreting part is extremely important to us, in fact, because this is the way our Earth was born. Because the debris that you were talking about, when the star is not too massive, I like studying very massive stars, many more masses, many more
times
masses,
the mass of the sun.
Times, thank you, Louisa. Times than the mass of the star, than the mass of the sun, and those stars don't form planets. But typically low and medium mass stars, they can form planets, and planets are formed in the debris of the accretion disk. So basically,
and that's how you get all the stars going in the same direction, or the planets going in the same direction in the same plane around the stars, because they were formed in the circumstellar disk.
The accretion disk is that the rotation that we've been discussing? Is it also called the accretion disk?
Yeah, it's the matter falls onto the disk, and then from the disk spirals into the star, and the star is rotating too.
Okay, because we talk about the gas clouds rotating in this,
but that's everything.
Video.
That's the central star and the planets and the disk, all of those,
and they all rotate because of gravity. Yes, please.
Everything rotates because our. Oh, I don't want to interrupt, Louisa.
No.
Actually, I don't know. So everything rotates because our galaxy rotates. So when the initial cloud forms, it starts with what we call in physics angular momentum. So it acquires a spin. And this is because our galaxy rotates. And so everything in our galaxy rotates. As again, the video was saying, everything rotates because the galaxy rotates. And so the initial cloud before the formation of the star is in rotation, is in motion. And then the accretion disk is also rotating around the accreting, the ball of gas and dust that is accreting. And the debris that form inside this accreting material, they also rotate. So these debris are the initial, initial sources of the planets. And the planets slowly, these are initially only rocks that become bigger and bigger until they become real planets. And so, and this is why. So, and they keep rotating until they create solar systems like the one that we see in our own case.
So like a skater pulling in her arms, a skater starts with both arms and maybe a leg out. And then as she pulls in those limbs, she spins faster and faster and faster and faster and faster. And so when you start with a big cloud of gas and dust, you're going to end up with something spinning really fast. And when people first started doing the math for that, they're like, well, I don't even understand how stars form in the first place, because it should be spinning so fast that it should rip itself apart. So all of that angular momentum, all of that has to go somewhere, and it's probably related to magnetic fields and maybe planet formation, because in our solar system, Jupiter is a massive planet fairly far out, and so it has the most angular momentum of just about anything in our solar system. So all of this matters. Keeping track of where all of the rotation matters for understanding how planets form.
Wow. Okay. Now, we've talked about there's, Roberta, you study massive stars, and then our star, the sun, is a smaller star and obviously created planets because we're right here. But how can we tell how old a star is? Obviously, we're not cutting it in half and counting the rings. This is not a tree.
Right. And you
How
can't
do
put
we
it in a
know?
lab. We can't put it in a lab and watch it from start to finish either,
So,
right?
yeah.
So the analogy that actually works way better than it has any right to is, imagine you're an alien trying to understand how humans form, right? So if you just picked a spot on the planet randomly, you'd hit water, which is not helpful, right? And you pick it again, and you'd probably fall on land. Again, not helpful if you're not in a city. Eventually, you'd find a special place in a city. And if you're lucky and you study the city enough, you might find a daycare center. And when you find a daycare center, the chances of you finding a pregnant woman goes up a lot compared to your average part of a city. And so you have to look in special regions like star-forming regions. And the amount of time a human spends inside their mother is relatively short compared to the time they spend as an infant, which is short compared to the time they spend as a toddler, which is short compared to the time they spend as a little kid, which is short compared to the time they spend as a teenager, which is short compared to the time they spend as an adult. And so that same analogy works. Those very earliest stages where they're real babies are hard to find. And when you look in a star-forming region and you finally find some, people get very excited because once you find one, you're probably going to find more. And then you can start to understand what these properties, the properties of these very youngest phases are. But when you find these star-forming regions, you tend to find more and more of the other kinds of stars, because the ones that are toddlers, because that stage is longer, you find more of them. And kids, that stage is longer. And so you tend to find even more of those. And the analogy even works when you get up to like late teenagers, early 20s, those folks look functionally indistinguishable from adults until you study them very closely and you realize they have more piercings and tattoos than the other adults. And once you study a youngish star, you realize, wow, this one's rotating much faster than the others and it has more star spots. So the analogy works way better than it has any right to, but it's the same thing. You try to study the formation of stars by trying to find as many as you can. And those very earliest stages are very hard to find, and they're masked because they're still inside the cocoon. So you have to be really clever about how you're going to learn about them. And it becomes easier the older the stars are because you can find more of them. And then you can have when you have more statistics, you have a better understanding of how long this phase takes and how it changes as a function of mass. And all of those things are easier the more you find. And so Spitzer, for example, increased the number of young stars that we know of by several orders of magnitude. So now we have a much better understanding of how all these stars, low mass stars form and what timescales and what stages they go through.
Okay, so we don't have all the information, obviously.
No, there's a lot of holes. There's a lot of things we don't understand.
But do we know like how long stars last? Like a person might live to be 110 years old. So now you can recognize a toddler phase of a star. You say, well, this probably has X billion years left in it. Is that that's real?
That is a function of mass. So the lower mass stars there are, the longer they will live. Really high mass stars live fast and die young.
Oh, interesting. I have a dark joke that I will not be saying. Look at me. Here, Roberta, let me ask you another question. Stars are too hot to have any dust within them. So what happens to the dust after the star forms?
So I think we touched a little bit about this early on when we talked about the accretion disk. So typically what happens to the dust is that the dust forms a cocoon within which the star forms and the accretion disk forms itself. But the dust basically tends to settle on the accretion disk. And that's where basically all the rocks slowly again become bigger and bigger and tend to turn into planets. Now, this is true in the case of low mass stars. For big stars, for high mass stars, this is not true. So for high mass stars do not form planets. High mass stars
Because they go
tend
too
to be
fast.
they go too fast, so they remain enshrouded in their dusty cocoon for their entire life, until basically they arrive to the main sequence, which is basically the stage that Louisa was mentioning before, when basically the star starts burning hydrogen into helium. So until that moment, during all the phase in which the star is let's say a baby and then a teenager, during all those phases the star is completely embedded in its cocoon, in its dusty cocoon. And in fact, I've been actually studying this dusty cocoon for a long time, and I'm really passionate about this. We can learn a lot about these massive stars just by looking at the dust. So we can learn how they reprocess the energy, how they re-radiate the energy that is actually coming from the embedded stars that are still completely hidden by this dusty cocoon.
And
So
the
this is
chemistry of the matter around the star is really complex. It's more than my brain can handle. It's really complex, trying to keep track of
Yeah.
all of the chemistry that are and how it's impacted by the star itself.
Yes.
Okay.
So basically, I think it's very important. A take-home message. It's that when we talk about star formation, it's important to think about two different categories: low mass star formation and high mass star formation. The scenarios are really different. It's like if short people. I'm a short person, so I'm in that category. But basically, short people live a life which is very different from tall people. This is very different from humans, but
Right.
it's a very true story for life, for stars. So short people and tall people are different, and
Sure.
which is not the case for humans, but it's true for stars. So low mass stars and high mass stars are very different. They were
Are
born
there
different.
yes, and they process things different, but do we know if there are more high mass stars than low mass stars? What are the
We
most
know
common types of stars?
the
Lots
low
and
mass
lots of low
stars.
mass stars. Yeah.
The
Okay.
high mass stars are very, very rare. High mass stars are extremely rare, but they're very important for the ecology of a galaxy. So they are the ones that basically kind of determine the energetic budget of the entire galaxy,
Because
when
these high mass stars explode, and then they kick out their
explode.
guts and the energy into the gas and dust.
So not
Oh,
only
good Lord.
they are born in a different way with respect to low mass stars, but they also die in a different way. So they don't die
Very
quietly.
spectacular.
Yes,
is.
in fact,
They will not go quietly into the night. They
That's
will
right.
take everybody out with them.
That's
And,
right.
Exactly.
Exactly.
They seem like
exactly.
trouble. So how long does like when you say shorter lifespan, longer lifespan, what kind of lifespan are we talking about here? A million?
So when
years?
I say I study young stars, I'm looking at things that are less than 10 or 20 million years. So that's really
Okay.
pretty young for stars,
That's a
but
quick
long compared to people. Yeah.
Right.
But yes, for stars like our sun, their lifetimes are much, much longer. But for stars that are high mass stars, they can be, a few million years, it can all be over.
Yeah. And even
Okay.
shorter. It can be like
Really?
100. Oh, yes. It can be 100,000 years and they are gone. So
Wow.
it's very short.
I do not wish to see a star go in immortality.
Oh, but it'd be
I
so
don't want to see the
cool. It'd
birth.
be so cool.
It's so cool.
Oh, excuse me. Both of you would like to see a star go from a safe distance, though, right?
Yes. Yes.
We'll have to do another episode about how stars explode, because this one was about how stars are born. Thank you so much for joining us to learn more about the science of the Universe Unplugged video think tank, A Star is Born. You can see that and all of our other Universe Unplugged videos at universeunplugged.org, or just click on the link in the comments. Subscribe on YouTube and you'll be the first to know when our next video comes out, and follow us on Facebook and catch our next live chat. You can watch all the old live chats that were recorded, of course, on that same page on Facebook. Until next time, I'm Jackie Cation, and this has been Universe Unplugged live chat. Thank you so much, scientists.
Bye.
Bye.